Okay, let's proceed to applications of the generative models. So we first will compare what we learned before midterm. No, before after midterm we learn. Before learning generative model, we learned lots of 3D stuff, right? Start with the multiple geometry theory, matching, camera calibration, structure from motion, multiple stereo, and then we learn mesh, point cloud, volume, implicit function, nerve, 3D Gaussian splitting. There are many things. So how does such kind of effort is different, and what is good point and bad point compared to these days generative models? And we will cover some basic generative models and these days 3D vision papers as well. So let's start with the how we got images so far. Before generative models, generative model is introduced in many years ago, but diffusion model is introduced in 2022. But before 2022, even these days, actually, how we get primary way how we got image is using rendering equation. We have 3D geometry. We learned, one of mesh, volume, point cloud, implicit function, anything is okay. We have 3D geometry and 3D texture, UV map, per voxel colors, per point colors, per Gaussian color, anything. And then camera, we learn intrinsic, extrinsic parameters and the projection way, perspective projection, orthogonal projection, or light, point light source, directional light source, BRDF. Using such kind of 3D assets, we can render images using rendering equation. This is the incoming light, and this is BRDF, and then this is dot product, so that you do not have to, this is computer graphics, so you do not have to fully memorize this equation, but we use this kind of rendering equation to get images, and this shows the output of structure from motion. We have cameras, we have 3D geometry, we have 3D texture, we have all the stuff so that we can render images, right? And then let's see how we animate. Let's see how we animate some characters in some current 3D computer vision and graphics pipeline. So first, 3D artists draw some canonical character. It is called rigging. 3D artists, they draw some character or object, anything in the canonical space. This kind of A pose or T pose is typical thing. And then they add some skeleton. They add joints. We have joints, right? We have joints so that we can move our body. We add joint, we add skeleton, all the things, and then it is ready for animation in the canonical space. And then we can use marker-based motion capture, or we can use markerless motion capture. Anything is okay. Markerless motion capture is we can estimate 3D human pose from images or videos. Anyway, we prepare some canonical character, and then we have some motion information. So, and then we combine them in mathematical way to get animated and rendered character. Render is usually we can use, there are many engines, Unreal Engine, Unity Engine, you can use any engines. Anyway, for the animation, we draw characters in canonical space, and then we have motion information either from markerless motion capture, marker-based motion capture, and then we animate character, and then we render it to image screen space. Using Gaussian splitting, mesh, or anything, we can use it. And then lighting, how we do lighting. This is typical way for lighting, image-based lighting, in short, IBL, image-based lighting. This is crumble. So the light, there are many light sources in this environment, right? How can we capture 360-degree scene then? This is the one way to capture 360-degree. We can prepare crumble. Crumble is chrome is the name of material, right? We prepare crumble so that crumble is reflection rate is almost 1, so that we can capture all the incoming light in the crumble, and then we can unwrap this crumble. We have sphere crumble, right? And then we can unwrap the crumble to the UV space. That is called environment map or HDR map. Image-based lighting is the very widely used these days for the lighting. We capture 360-degree scene using crumble, and then we unwrap this captured 360-degree scene to the UV space that is called environmental map. And then we can use this unwrapped environmental map for the image-based lighting. we put 3D geometry with its texture inside of sphere. Let's, assuming our environment consists of very huge sphere. Let's say our environment consists of a very huge sphere, and then we can put some 3D geometry inside of sphere, where and each sphere this is unwrapped UV maps, right? So then we can put this UV map on the sphere, right? And then each light source, all this point on this sphere becomes light source, so that the direction of light is a normal vector of sphere, and then the color of light is from this UV map pixel, so that we can, and then based on rendering equation, we learn rendering equation, right? BRDF, what was that? The normal vector, and then dot product, incoming light, and incoming light is from this one. So this is typical way for image-based lighting. Why we call this image-based lighting is that this is image. This is UV map is image, so that we call this image-based lighting. We have UV map, and then we wrap this sphere with this UV environmental map, and then each point on the sphere becomes light source, and then where the light direction is normal vector of sphere, and then color of light is from this pixel, so that we can get this kind of light rendered with light. That is a typical way for the image-based lighting, very widely used these days. Of course, there are many kinds of light. The point source light, distant light, spot, area. There are many lights, but these are some very narrowed lights. But for this environmental map, it gives a global light. And let's see this video. So that using this kind of computer graphics technique, even these days we use computer graphics technique in many places, right? In AAA movie, AAA video game, all these virtual characters are rendered with rendering equation. Of course, here are many markers when the actor is spotted, right? But we can replace markers with markerless motion capture, for example, using 3D pose estimation from images. But still, we use rendering equation to get image. That is the actually, except for just manually drawing with our hand, this is the only way we can get images so far. Using 3D geometry, texture, camera, light, and then using rendering engine, we can render images. And then these are widely used in these days and standard in industry, computer graphics. So in summary, 3D computer vision and computer graphics, it relies on rendering equation, 3D geometry, texture, light, camera. We learn this instead, except for light, we learn all the things are needed to get images. That means getting images is a little bit hard. We need to prepare geometry, texture, light, camera to get view consistent videos or images. But this kind of 3D assets, 3D geometry, especially 3D geometry, gives us view consistency. That means we exactly know which rendered image we will get, as we know everything in the 3D space, right? We know 3D geometry. Then, it's mathematically guaranteed that, we know which rendered image we will get from such kind of 3D assets. We know everything about 3D space. And it is very safe for production level outputs. It is mathematically guaranteed that we know everything about 3D scenes, so that we exactly know what will happen when rendering. There are gonna be no monster-shaped rendering. All the rendering will be safe, so that it is widely used in production level outputs. For example, movie, game, commercial, everywhere. And actually, it's easy to edit. For the editing, for example, if you have some 3D geometry texture, but you want to change its color, how can you do that? You can keep others remain, and then just change the texture. For example, if you're working on mesh, then you can just simply change colors in the UV map while keeping the geometry, color, light fixed, right? It is all the components are disentangled and mathematically guaranteed that which we will get is very safe and quite widely used these days. Generative model, quite different. These days, image generative model know almost everything about real-world image distribution. As it is trained on huge amount of billion-scale images, it knows almost everything about real-world image distribution. Then, why not just skip 3D stuff? Why not just, typically what we want is just images. What we want is, for example, For example, let's see this example. What we actually do not need 3D stuff. All we need is always images, rendered stuff, right? All we need is always rendered stuff. Then why not just keep skipping? Why not just skip 3D stuff and then directly animate images into this image space, directly rendering images, low-value images, while skipping 3D stuff using generative model. That is these days approach. To directly synthesize low-value, low-value pose images from input image instead of constructing 3D assets. The drawback of 3D assets is that it is hard to get. Let's say we have a single image, we cannot get 3D geometry, we cannot 3D texture because of we know, right? We have depth ambiguity, scale ambiguity. From single image, there are many ambiguities to get 3D stuff. So instead of constructing 3D assets, why not just directly synthesize low-value, low-value pose images using generative model? Because image generative model knows everything about our real-world images. That is these days image generative model's approach. Especially training set for image generative model is relatively easy to get. For example, instead of, we do not need to collect 3D assets. For example, if we can just collect images or pairs of image and text. Assuming we have infinite amount of time and money, then we can collect huge amount of data. We have lots of images in social media, Instagram, YouTube. We have lots of images and videos. We do not need to get 3D notation from such kind of images and videos. We already have huge amount of images on the web, so that we can directly use them instead of constructing image and 3D paired data set. That is the philosophy of these days image generative model. So in summary, 3D computer vision graphics requires 3D assets, geometry, texture, light, camera, and it uses rendering equation. But the limitation is that such 3D assets are hard to get. Let's say we have a single image, we cannot get 3D geometry, we cannot get 3D texture because of depth and scale ambiguity. We need at least 2 view images, right? That makes data collection quite expensive and non-trivial. But the good point is that view consistency. Anything is consistent. We know what will happen when render some images from some certain camera pose. Mathematically, it is guaranteed that we will get some images. So we know which rendered image we will get, and it is safe for production level outputs. And image generative model or video generative model, it does not require 3D assets and only require casual inputs like text prompts. That is good point, definitely good point, especially for our user case, our user end, we want some images from text prompt. Text prompt is quite easy to provide, right? We can just type some text prompt. They're very easy to provide to system. So it's a very good point of generative model, but the drawback is that inconsistency, unfortunately, because it does not rely on any 3D geometry, so that we do not know which rendered image we will get. And not safe for production level outputs. Rendered image often have artifacts, and I guess this shows the typical failure case of generative model. These are from Sora 2 and VO3. VO3, Sora 2. These are highly advanced state-of-the-art video generative model these days, but still have this kind of hilarious failure cases. So as you can see from this one, this guy is jumping on the trampoline, but when he falls down, there's no water on the trampoline, but then there is a water when he fall back to the trampoline. There's a water on the, next to the trampoline, but this is, of course, something is weird, right? And this one, a woman is punching on the air. It does not hit the light, but the light falls down as if she punched the light. Or here, there are many people, and then people are jumping together, but suddenly a new person came out, and then the new person just fall down. That is, of course, some failure case of generative model. And then this one, a guy is riding a horse and then fall down, and then suddenly he jumped up. The ground plane is just the rock. There's no trampoline, but suddenly this guy is, jumping up after falling down. This is, of course, physically implausible. And there are 3 arms, right? 3 arms. So there are many inconsistent outputs. So of course, this visual diverse and visual photorealistic realism is very good, but still, this kind of VO3 Sora 2 state-of-the-art generative models suffer from this kind of inconsistency. That is drawback of generative models. So that I think there are, so this is my personal opinion. 3D vision, computer graphics have high structured, consistent representation. It is hard to get training data. And then generative AI these days, unfortunately, not very structured and not very consistent, but easy to get training data. We do not need to label. We only need image and videos, that's all. That is good point of generative model. We only need to use lots of data, because what we are interested in is data distribution. We do not need to prepare 3D assets. That is good point of generative model. And then, these days, people are trying to incorporate 3D vision and generative AI, and that word model is, I think, one of the example for combining this kind of consistency from 3D vision and then generative models, diversity and photorealism. Word model. I'm not sure you've heard this word model. That is from Google's Genie 3. Google's Genie 3. So this one is, generative video, but user can interact within the video. These are keyboard input, real-time keyboard input. As if it is a video game, we can control some agent in the video in real time. But the challenge for this task, this is very interesting and that very promising research direction, I think. But the one of challenges that we need to make consistent rendering. There should be, there are many viewpoint changes. All the things should be view consistent. There should be no physically implausible stuff. We need to make this generative video consistent and physically plausible, right? That is main challenges for this one. And anyway, word model is one of the example that these days people are trying to incorporate 3D vision and generative AIs. So that I think these are complementary relationship. 3D vision provides structured and consistent representation, but getting training data is a little bit hard because from single image we cannot get training data. We cannot get training 3D assets. But on generative AI, it is a little bit not structured and not consistent, but getting training data is easy, right? So they are complementary relationship. And how to combine them is open research problem. How can we combine them? Especially consistency and physical plausibility from 3D computer vision. And generative AI, easy to get training data, and good photorealism and diversity. How can we combine them? That is open research problem. I think it's quite interesting, right? Let's proceed to dream diffusion. This is the generative model presented at iClear 2023. This is the, anyway, anything is unclear about the comparison between 3D vision and generative model? Is okay? Okay. Then Dream Fusion is presented in 2023, iClear. It is one of the first approach for text to 3D generation, only using 2D diffusion. And this shows the qualitative result. As you can see, the quality is actually a little bit limited, not very good, but this one is almost one of the first attempt to achieving text to 3D generation. And so as I introduced image generative models, they are trained on huge amounts of text to image pairs, right? And such pairs are much easier to get than text and 3D geometry texture pairs. So that is the motivation of this work. Instead of collecting expensive data set, how can we utilize image generative model, pre-trained image generative model for the text to 3D generation? But how can we extend the image generative model to 3D space? So Dream Fusion, this paper proposes a score distillation sampling, in short SDS. SDS uses text as a guidance to optimize images to be aligned well with the text. These days actually not used pretty much, but was a very interesting approach at that time. So in short, in one sentence, Dream Fusion tries to optimize a nerf for each text prompt using SDS laws. That is what this paper tries to do, in short, in one sentence. We learned nerf, but let's recap the nerf again. This is from the previous slide. It is trained with the only supervised render image with image loss, without 3D geometry ground truth, without 3D ground truth. We only optimize NeRF with the image loss using volumetric rendering equation. We have MLPs, and then MLP takes the position and directional information, and then outputs color density, and then volumetric rendering, and then we compare the rendered image and ground truth image, and minimize image loss to optimize weight in MLP. And then this one shows the volumetric rendering equation. We cast from the target screen space, we cast ray, and then we perform ray marching, and then so that for each marched ray, we check whether it is occupied or not, and then we accumulate the density by using this one integration, and then we keep multiplying, keep accumulate the color density during the ray marching, and then we get image. That is the NeRF. And then, so the first stage is it randomly initialized MLPs and NeRF. So NeRF consists of some MLPs, right? So we randomly initialize MLPs in NeRF. The weights of MLPs are optimizable. And then with random light and camera, so here are lights and camera, we render images using NeRF. That is a typical NeRF. There's no special thing. And then we have some render image. Of course, at the early stage of training, this rendered image will look like a noise because the weights of MLP are just randomly initialized. So the rendered image will be, there's nothing semantically plausible thing, just some arbitrary image, right? At the early time of the training. And then during the training, we have a estimated density and albedo. And then from density gradient, we get normal, and then light is shading is obtained by dot product. This is just rendering equation, normal and light dot product, so that we can get shade. And then element multiplication of albedo and shading, we can get color. And then we render it. That becomes rendered image. And then we perform forward diffusion process. Forward diffusion process is, as I said, just adding noise to the image. There's no neural network, just adding noise to the image, and which is used in training stage diffusion model to the rendered image, so that becomes this kind of noisy image. And then we have pre-trained denoising network. Maybe we can use some denoising network of stable diffusion or anything, that's okay. And then we provide the noised image to the pre-trained denoising network, and then it outputs some noise, right? And then this one shows the diffusion model, as I introduced. This is forward diffusion, and this is reverse diffusion, and this is the where neural network is doing. So we get rendered image, and then we add noise. That is, adding noise is forward diffusion, and then we pass this noised image to the denoising network to get estimated noise. That is reverse diffusion. And then compare, and then we have estimated noise, estimating noise here, and then we have epsilon hit, and then we have ground truth noise, and then our goal is minimizing this one. Our goal is minimizing the distance between this one. So if the image is, if image looks like image is almost the same as this text prompt, then the epsilon hat and epsilon might be almost the same, right? But if image is very far from this text prompt, epsilon hat and epsilon might be very far. So that is the main motivation of this core distillation loss function. This shows the SDS loss. If image is well aligned with the text prompt, then estimate, because this denoising network is trained enough so that if image and text prompt align well, then estimated epsilon hat might be very close to injected epsilon. That is the motivation of this SDS loss function. So we minimize distance between estimated epsilon and epsilon, and then we can get gradient from such kind of loss function, and then we backpropagate that gradient to the MLPs in NeRF. That is the main philosophy of SDS loss function. So it is quite smart way to utilize image generative model to optimize 3D stuff. We rendered, by rendering 3D, by rendering NeRF to the image space, we can get image space so that we can do something in the image space, and then, but there's no ground truth, there's no reconstruction loss, unfortunately. We have only text prompt, right? then how can we measure the similarity between text and image? That is the one way to measure similarity between text and image using image generative model. If image is very aligned with the text prompt, then estimated epsilon hat might be very close to epsilon, because this UNet is pre-trained on lots of images, so that we assumption is that UNet performs well. If assuming UNet performs well, then we can say that if image is aligned with the text prompt, then estimated epsilon hat might be very close to epsilon, so that we can get, all this operation is differentiable, right? So that we can get gradient from this loss function, and then we can backpropagate backpropagate gradient to nerve weights, so that we can optimize the MLP. That's the main philosophy of this SDS loss and diffusion dream fusion model. So we calculate gradient to minimize distance, inject estimated noise, and then that is all the things are differentiable, so that we can backpropagate gradient to the nerve, that is SDS loss, and then we optimize MLPs in nerve, so that we keep repeat doing this. But as you can see, we optimize nerve for each text prompt using SDS loss. That means a nerve is dedicated to only this text prompt. This is not generalizable system. This nerve is only optimized for this text prompt. If you are interested in another text prompt, you need to train again, and then you can render it. So that it is, once we can train, this nerve is only for this text prompt. If you change text prompt, totally change text prompt, then you need to train nerve again. So there are actually many limitations. We cannot use pre-trained nerve for other text prompt. That is, of course, definitely limitation. But this is one of the earliest approach for utilizing generative model for the 3D generation, and quite smart. Actually, there's no novel training stuff, right? Optimizing nerve is introduced in nerve work, and then this one they use pre-trained UNet, pre-trained denoising network. And they do not fine-tune UNet. There is no fine-tuning at all in the diffusion side. So it is actually the only computation they need to use is just optimizing nerve, so that it is quite a smart way to use pre-trained image generative model. Also, image generative models are also pre-trained only on images without 3D assets, so that this work does not require any 3D assets for the text to 3D generation. Only use image generative model. Image generative model itself is also trained only on images without 3D assets. So without using any 3D assets, this work shows possibility for using image generative model for the text to 3D generation. But if text prompt is slightly changed, for example, start with a squirrel, and then, for example, wearing a leather jacket, riding a motorcycle on a road made of ice, it is slightly changing, right? Then we can reuse nerve, we can optimize nerve with this one, and then we can reuse the weights of nerve by changing text prompt slightly, and then we can keep optimized nerve, right? In this way, we can reuse it, but totally changing text prompt, for example, generate a apple and generate a dog, that is totally different, right? Then in that case, we cannot reuse nerve. But if text prompt is slightly changed, then we can reuse nerve weights. So these are comparison to previous work at that time, 2023. At that time, text to 3D generation was not mature at all, so the image quality is not very good. But the important thing is that they show the possibility for performing 3D generation without using any 3D assets. That is quite interesting approach, I think. Anything is okay about the dream fusion? And 0, 1, 2, 3. The naming is very fancy, right? 0, 1, 2, 3. 0, 1, 2, 3. Naming is quite fancy. Zero shot, one image to 3D object. So one image to 3D object, that is, you can understand, right? That we have only single image, and then we want to lift it to 3D space. Zero shot means, we do not use any annotation of any images. Just a single image is enough. For example, few shot means before testing, we need few paired data. few shot. Few shot means before testing, we need a few amount of image and ground truth pairs. That means few shot before testing. But on zero shot means before testing, this work does not need any paired data set, directly generalizable to arbitrary image. That is zero shot. So that there's a 0, 1, 2, 3. And this one shows the result. This is present ICCP 2023. As you can see, the image quality is much better than previous one, right? But the task is slightly different. The Dream Fusion, the goal was generating 3D assets from text prompt, text to 3D, but here it's image to 3D, image to 3D. And you can see the input and synthesized ones. And the 0, 1 to 3 train a LDM model. We learn LDM model, right? Latent diffusion model. That takes the input image and camera extrinsic for novel synthesis. And does not rely on any 3D geometry. Mesh, point cloud, volume, does not rely on anything. The Dream Fusion relies on NERF, right? But here, 0, 1 to 3, it does not rely on any 3D representation. So that so here it shows the pipeline. It has input view image RGB and then camera extrinsic RT. We learned camera extrinsic, right? Rotation and translation of camera. We pass this one to latent diffusion model with Gaussian noise, and then it outputs corresponding image of novel view. That is very interesting, right? In classical way, what we need to do for this is that we first need to reconstruct 3D assets from input view image, right? We need to reconstruct mesh, volume, anything from input image to 3D space, and then we have camera parameters so that we can render some new image using from reconstructed 3D assets. That is a classical way for getting low-level images, right? But this one, there's no 3D reconstruction. There's no, just camera model. Just directly pass all the things to the latent diffusion model to get output view image. It's very interesting, right? Very different from what we've done so far. What we've done so far is just using 3D, totally based on 3D representation and then render images. But this one, all the things are in the latent space. There's no 3D reconstruction at all. So in short word, it learns to render new images. This kind of, 3D reconstruction, rendering is, all the things are based on mathematics, right? We know rendering equation, we know all the things in the mathematically, but this one, it skip all the things complicated detail. We skip all the things, all the mathematics, just learn to render new images in a data-driven way. A very interesting work. Of course, we can, using 0, 1 to 3, we can generate novel images from input image, and then using generated multiple images, we can optimize NERF and 3D Gaussian splatting on generated images. That is also, of course, possible. So what we do is that we fine-tune pre-trained image generated models. This is stable diffusion, introduced CPR 2022. The original stable diffusion takes text prompt and output image, right? It's text to image model, right? So there's a conditional text. So but this one, there's no text prompt, just input image and RT. These are conditioned. So it fine-tuned pre-trained stable diffusion. It removed text prompt, but it adds image and RT here as a conditional information. That is all actually. It brings pre-trained stable diffusion model, and then it removed the text prompt, and it just replaced text prompt with the image and camera extrinsic to get novel images. For the training, they use synthetic data sets. This shows this is not the exact data set they used, but synthetic data often consist of this kind of assets, like a many object, maybe made by 3D artists. These are maybe can be used in 3D computer graphics, but using this kind of 3D assets, we can render new images using virtual cameras. We can set virtual cameras. Maybe, for example, we can make a look at camera, which object is here, and then we can virtually place many cameras around object, right? And then we can render new images. And then for the rendering, we need to know camera intrinsic, we know extrinsic, right? So that in the data pre-processing stage, we know everything for the training. We have 3D assets, but we set virtual camera using camera extrinsic, and then we render image. Then rendered image and camera pose becomes input of 0 to 3, that's all. So that we render 3D assets to multiple images and use rendered images for the training. This one is from lecture slide 14, and here we have synthetic image. This one, 0 to 3, it utilize synthetic images. Because in the world image is, of course, better. It has real object, and light is very natural. All the things are very good, but the problem is that we cannot render multiple images from in the world image, right? So that 0 to 3 cannot use in the world image. Multiple studio image, light is too fixed. There is no diversity. Background is always fixed, so that light is always fixed, but it is not very diverse, so that they use synthetic image. And this one shows the outputs of 0 to 3. They can use 2 views or just 1 view, 2 view. You can see the quality is much better than previous work. This is also one of the earliest approach for generating low-level images without relying on 3D stuff. So the quality is a little bit limited actually, but compared to competitors, the quality is much better. And here they also use 2 views, and the quality, you can definitely note that the difference between rendered and ground truth is a little bit different. And then here it takes a single image and render new images. It's very interesting. It does not require any 3D reconstruction, just use capability of image generative model so that it learns to render new low-level images from input image. It's very interesting. And there's a normal Gaussian. So here we have Gaussian here. We have Gaussian noise, right? Gaussian noise is, for each sampling, we can randomly sample Gaussian noise. That means we can, for each inference, we have different inputs to system. That means different output from system. So this is input image, and then while the camera parameter and input image is the same, we can provide different Gaussian noise to the system that produces different images, right? This one actually a little bit weird. There should be some length in this side, but anyway, it can produce low-level images, different low-level images, although input image and camera parameter are the same. And here as well, so input image. This one I think makes sense. The backside of car is not shown in the input image, but it produces diverse types of images from the same input view and same input image, same camera extrinsic parameter. And geometry reconstruction. So from generating multiple images, we can do anything, multiple stereo or nerve optimization, Gaussian spectrum optimization, anything, so that we can get 3D geometry like this. Much better than competitors, I think. But this geometry is actually not very good, but still much better than competitors. So as you can see, when you do research, you need to do the you need to do the unexplored thing the first time, because the quality itself is not very good, but because there have been no work that have tried to do this. The quality is not very good, but the paper is accepted, and then it got many notice, so that you better start some unexplored thing instead of doing the task that many people are doing this. And text to 3D. So originally it takes image to 3D, right? Image to 3D. But we can do text to 3D as well. Text at that time, DALL-E 2, I can't remember, maybe OpenAI, I think. Maybe. Text to image. These days, Nano Banana from Google is much better, but at that time, DALL-E 2 was very good at that time. So text to image, and then we can get some image, and then we can pass image to 0 and to 3 for the image low-level synthesis. So here, it is, a little bit unclear. We can call this 3D generation because there is no 3D geometry Of course, based on generated motif images, we can optimize geometry, but model itself does not generate 3D actually. It just performs low-level synthesis, not generating 3D geometry. But in many cases, actually, what we want from 3D is low-level images or low-level pose and images, low-level light image, so that in this context, maybe we can call this a 3D generation as well. But unfortunately, there are many failure cases. This is often called Janus problem. Viewpoint generation biased in diffusion models. So here you can see this crocodile has 2 eyes, but if you change the viewpoint, there are 3 eyes. Of course, this is not what we want. Or this one, you can see the backside of the rocket is not very good. Or here you can see there's some weird rope here. So all the things are data-driven way. Data-driven means mathematically we cannot guarantee anything, and this kind of thing can happen. So that is the reason why these days in industry, computer graphics still widely used. Rendering education is still standard, because imagine you make a movie or commercial, but your users see this kind of weird-looking images. That is absolutely not what we want. We want very safe technique, and then we need to guarantee all the things. Nothing weird should happen. So that is the reason why rendering education is still widely used in industry. But performance of generative model is, doing better and better. So that maybe in someday people might not use rendering education and use this kind of generative models. But as I said, we need to but still people try to incorporate this kind of 3D stuff and generative model, and one of the examples is word model. Anyway, there are many typical failure cases here, because all the renderings are based on data-driven way. So okay, that's the end of today. And anything you want to ask? Anything is unclear? Okay, then let's check the attendance and finish.